chapter 2.6, exercise 4, part C, where we're going to, now that we have solved by separation of variables for an actual solution, the explicit solution, now we're going to modify our code to include that here to measure the percent error between Euler's method and the and the actual solution. So let's do that. Let's go over to MATLAB. This was our code. Now we'll have to define a couple things, so bear with me. Let's define our actual solution in the code, in the loop, defining the actual solution. So y naught of n plus 1 is going to be equal to what? Well, it's going to be equal to, if we have the actual function, we can just input our x. So that's going to be exponent of x squared minus 1. And the x that we're going to input is that same x that we're using here, right? Well, not so fast. We're going to have to input, because this corresponds to x of n plus 1. So we're going to have to input x of n plus 1, but we haven't defined it yet. X of n plus 1 happens to be this one. So we want to define this one down here. Otherwise, it would not work. And I'm doing this with you, so I might make mistakes. This is the actual solution, right? Because this is telling me what I need to do to x in order to make it my actual y. And this is my n plus 1, which corresponds to a y plus 1. Now, there is something, well, we need to start with a value of n, so we can say y naught here, y naught of 1, well, that's going to be the same, because we're assuming we were starting from something that we knew. So y1 is the same as y naught 1. But then we're going to get different things here. So we're going to define an n plus 1 here. Well, now we don't need this n plus 1, because we have, this was y sub n, and n plus 1, this is going to be 2, and this 2 is going to happen when we have this. So it's just going to keep appending on this. And now we want to find measuring the error. So let's just call this the vector error. And that's going to be equal to our y of n, and this is where the indexes get weird, because now I changed n here, so n plus 1 is really y of n now, plus, well, minus y naught of n, and then we wanted the absolute value of that, right? Absolute value, I don't know if that's how you do it here. I'm going to have to check in my command window. Is there a command for absolute value? Yes. Okay. See, I love how MATLAB is intuitive sometimes. So we want the absolute value of this divided by what it should have been, and what it should have been was y0 of n, because that comes from our actual solution. And then what? And then we want to multiply it by 100 because we want it as a percentage. Okay? So I think this would do the trick. Let's press Control Enter and let's see what happens here. And we don't want all these nasty fractions to appear. So first of all, let's put a comma here, a semicolon, so that it doesn't output. And then we'll say that this error needs to be an approximation. And now let's clear all those outputs and let's try again. So the code ran. Now we'll go over here and I'm gonna ask it to output the error. And now the error, okay, so I notice here there's a little bit of a mistake. I get just one value, and that is because, right here, I get just one value. That is because I didn't index this variable. So let's put x sub n, and our initial error, I'm gonna have to get error 1, that is 0. So let's go over it again. I'm going to press Control Enter. Now the error also has 11 numbers. So now I'm going to ask it to output error again. And we see we have all of these right here. And this is just 7% error, 1.4% error, 2%, 3%, and as we get away from that initial point, we get more and more error, which kind of fits the intuition of the drawing here. We get farther and farther from the actual solution here. And now let's see if we get smaller values, if we are to say put, or higher errors, if we put 0.1. Let's see. This code is executing again. Now I'm going to put error here. And see, the first one already has a 2.7% error. The second one at 5.7. So the error gets larger and larger. So we did our job. Now we could take these and put them into a table. I thought this was very useful. Also as a way to kind of reason through codes and how to modify a code. And also to understand that Euler's method is good if we have small x, small h's, which kind of fits the idea that if we get smaller here, we get closer and closer to what the actual value of f of x would have been. I hope this was useful, and I will see you next time.